Okay, in this module, we're going to be building on the modules that we did this week or the previous modules, which is the start e-transform. And what we're going to introduce is the concept of the pulse transfer function. Now, to see why this pulse transfer function is important, later on, we're going to be designing a controller. Now, if I have a system that I want to design a controller for, let's look at this system that we have here, and I want to design a digital controller for this system. This is an analog system. One thing I can do is I can do a controller, an analog controller, which I have here in this block here, C of S, and then I can approximate this analog controller to become a discrete or a digital controller. So I can do a discrete approximation of this analog controller and replace this analog controller with an analog to digital converter, a digital controller, and then digital to analog converter. So these blocks will approximate the continuous time analog controller. So this is one approach for design the controller. Now the second approach is the direct design. And in the direct design, I'm going to just design the controller. I'm going to take the output of the controller, convert it to an analog signal, apply it to the plant, take the output of the plant, convert it to a digital signal, and then feed that signal to get the error signal. So my error signal here is going to be E of Z. Now, which one of these two approaches more powerful? As we will see, this direct design approach is a more powerful method of designing a controller for our system. Now, in order for us to design this using a direct design method, I need to be able to take the transfer function between Y of Z and U of Z. If I look at this system, I want to be able to calculate G of Z, which is Y of Z, over U of Z in this figure here. Now that is not straightforward because this GP of S is an analog plant. So this plant here, GP of S, is expressed in terms of S. It's a continuous time system. However, I want to be able to get the equivalent of the output Y of Z, which is if I were to take the output of the plant, convert it to a digital signal. If I were to take the digital signal that is coming out of the controller, convert it to an analog, I want to be able to find the transfer function between Y of Z and U of Z. And therefore, this is going to be what we're going to be calculating or introducing in this module. How to calculate G of Z, that is Y of Z, over U of Z. Okay. So with that, start our topic, the pulse transfer function. G of Z. Now this pulse transfer function is the ratio between the Z transform of the output sequence Y of K and the input sequence U of K. Again, from this graph, the output sequence Y of Z, it's a discrete sequence Y of K, Y of Z, discrete sequence U of K. The ratio between the two is going to give me G of Z. G of Z, of course, the ratio of the Z transform of both. G of Z is going to be Y of Z divided by U of Z, where Y of K is equal to Y of T at T equal to K multiplied by T, and similarly U of K is equal to U of T at T equal to K multiplied by T. So therefore, we can use the pulse transfer function. If we are given U of K, we can calculate the response of the continuous time plant at the sampling instances. So this is why we need this G of Z. So let me write this down. Given U of K, which is the input that we have here, if I have the input here, which is the output of this controller, and G of Z, which is the pulse transfer function, we can calculate Y of K, which is the response of the continuous time system at the sampling times. The continuous plant GP of S GP of S. Okay, so of course it's important to remember that, or keep in mind that when we calculate this output Y of Z, that is going to give us the output only at the sampling time. Between the samples, we know nothing about the response of the system. So again, when I look here, if I calculate Y of K, I'm gonna know the response at this instance in time, at these sampling times. Now what happens between this sample and this sample, I have no access to if I'm looking at Y of K. Okay. So let's start the derivation of G of Z in terms of GP of S. And let's look at this block diagram here. Let's consider the block diagram below. So what we have here is we have digital to analog converter, a zero older hold digital to analog converter. So we represent this with the zero older hold transfer function, G zero older hold. And we have at the input a discrete sequence U of K, or U star of T, and these will have U star of S. And here we know that U of Z is equal to U star of S, and all I have to do is to replace E to ST with Z. So here I have discrete sequence U of K. I can also label that as U star or U star of S. Now at the output, I'm gonna get a continuous time signal, because this is digital to analog converter. It's gonna give me U bar of T, which is gonna have a Laplace transform that is U bar of S. Now this signal is gonna go to a plant GP of S, which is a continuous time signal, a continuous time system. Now what I'm going to do, I'm going to sample this output. So the output Y of T is continuous. It's going to have Y of S. And once I sample it, I'm going to get Y star of T, and I'm going to get Y star of S. Now again here, Y of Z is going to equal to Y star of S with E to ST equal to Z. Again, this is similar to the system that we started with. We have U of Z, digital to analog converter, the plant analog digital converter. We took some of these components. We have the zero older hold. We have the plant. We have the sampler of the analog to digital converter. and we're trying to calculate the transfer function g of z between the output y and the input u. Okay, so we know from previous modules that this zero order hold has a transfer function that is 1 minus e to negative s multiplied by t divided by s. This is the transfer function of the zero order hold. Okay. And what we are trying to get is we want g of z that is equal to y of z divided by u of z, which I can write as y star of s divided by u star of s, and I have to replace e to st with z. To replace e to st with z, yes. So again, looking at this system, I'm going to calculate g of z that is going to relate the output y to the input u. This is discrete and this is discrete, and therefore I'm going to get g of z, y of z over u of z, and this is going to equal to u star of s divided by u star of s. Okay, so if we look at the block diagram, we're trying to calculate, we see that y of s is equal to gp of s multiplied by u bar of s. So here, y of s, this output here, is equal to gp of s multiplied by u bar of s. So this we can write as gp of s. But what is u bar of s? If I look at u bar of s here, it's nothing other than the output of the zero order hold, which I can calculate easily by multiplying the transfer function of the zero order hold with the u star of s. The u star of s is the input multiplied by the transfer function. So this multiplied by the zero order hold is going to give me the output u bar of s. So therefore, looking here, this is going to equal the zero order hold multiplied, of course this is of s, multiplied by u star of s. And this is equal gp of s multiplied, what is the transfer function? The zero order hold, 1 minus e to negative s multiplied by t divided by s multiplied by u star of s. Now we are stuck. How can we simplify this? And in order to simplify this, we need two relationships. So let me write these relationships, and I'm going to prove them, and then we're going to be using them. So the first relationship says that if y of s is equal to p of s multiplied by u star of s, then y star of s is equal to p star of s multiplied by u star of s. So this is the first relationship that we're going to be using. And the second relationship says if y of s is equal to 1 minus e to negative s multiplied by t multiplied by a function p of s, then y star of s is going to equal to 1 minus e to negative st multiplied by p star of s. Okay, so these are two new relationships that we will show how they came about. So let's look at the first one. So consider y of s equal to p of s u star of s. Now we know from the star transform that u star of s can be written as 1 over t, the summation from n equal negative infinity to infinity E of s plus j n omega s, where omega s is equal to 2 pi over t. This is one of the three expressions for E star of s. So therefore, using this, if I substitute for E with y, I'm going to get y star of s is going to equal to 1 over t, the summation from n equal negative infinity to infinity. And I'm going to substitute for y. What is y? P multiplied by u star. So this is going to be P of s plus j n omega s multiplied by u star of s plus j n omega s. Again, y equals to P multiplied by u star. So all what I've done is I substituted for y star is going to be y star is going to equal summation of P multiplied by u star. Okay. Now, if I look at this u star is periodic. U star of s is periodic. So therefore, u star plus j n omega s is equal to u star of s. So I can come to this expression. I can write this as y star of s is equal to 1 over t summation from n equal negative infinity to infinity P of s plus j n omega s multiplied by u star of s. Now what is this equal to? If I look at this expression, what is this expression? 1 over t, the summation of P of s plus j n omega s. This is nothing other than P star of s. So therefore, I can write this as P star of s multiplied by u star of s. And therefore, y star of s is equal to P star multiplied by u star of s. Okay. Now let's look at the second expression that we have. So let's consider that if we have y of s equal to 1 minus e to negative st multiplied by p of s. And what this says is that y star is going to equal 1 minus est multiplied by p star of s. So let's see what that is going to, how we're going to show that. Y star of s is going to equal to 1 over t, the summation from n equal negative infinity to infinity 1 minus e to negative s plus j n omega s multiplied by t multiplied by p of s plus j n omega s. This is the expression for y star. Y star is equal to 1 over t y of s plus j n omega s. Now what is this equal to? We can write this as equal to 1 over t, the summation from n equal negative infinity to infinity, and this is 1 minus e to negative, this parenthesis the t should be outside, so 1 minus e to s multiplied by t multiplied by e to negative j n omega s multiplied by t multiplied by p of s plus j n omega s. Now omega s multiplied by t, this is going to equal 2 pi divided by t multiplied by t, which is equal to 2 pi. And therefore, if I have e to negative j n omega s multiplied by t, this is going to equal e to negative j n multiplied by 2 pi. And this is going to equal to cosine of negative 2n pi plus j sine negative 2 pi n, or 2n pi, which is going to equal to a 1. So therefore, this expression here, or this term here, is just going to equal to a 1. And therefore, continuing, y star of s is going to equal to 1 over t, the summation from n equal negative infinity to infinity, 1 minus e to negative, and there is a negative sign here. There is a negative sign. 1 minus negative s multiplied by t. This term is 1 multiplied by p of s plus j n omega s. Now I can take, since this does not have any n in it, I can take that out. I can write this as 1 minus e to negative st multiplied by 1 over t, the summation from n equal negative infinity to infinity, p of s plus j n omega s. Now looking at this, what is this equal to? 1 over t summation of p of s plus j n omega s. This is nothing other than p star of s. And therefore, I can write y star of s as equal to 1 minus e to negative s multiplied by t multiplied by p star of s. And this shows the second expression that we're going to be using. Okay. So going back, this is the expression that we're trying to simplify. And therefore, if let's go back to it, we have y of s equal to gp of s multiplied by 1 minus st divided by s u star of s. If I use equation 1, so this equation 1, this is 2. If I use 1, then I can write y star of s as equal to GPS 1 minus e to negative st multiplied by gp of s divided by s multiplied by u star of s. How? I need a star here. So here, this relationship tells me that if you have y function of s multiplied by u star, then y star is going to equal that function multiplied by a star, granted that this term has a star in it. So this stays as is. Y star is going to equal p star multiplied by u star to get you y star, and that is what we used here. This term already have a star, so if I take all this together as one function, if I take y star, is going to be star of this expression between parentheses multiplied by u star. Okay. Now, if I apply the second relationship, I'm going to get y star of s is equal to 1 minus e to negative st multiplied by gp of s divided by s multiplied by u star of s. And this comes from the second relationship that tells me if you have y 1 minus e multiplied by a p of s, then if you calculate y star, then p is gonna become p star. So therefore here this used to be u star, okay. So again, if I take 1 minus e to negative st multiplied by gp over s all star, I can take 1 minus e to st and just maintain the star to the second term. Okay, so from here, if I substitute z equal e to st, I can write this y star. If I replace e to st with z, I'm gonna get y of z equal to 1 minus z to negative 1 multiplied by gp of s over s star, where e to st is equal to z multiplied by u of z. So u star, y star is going to become u of z. E to st is going to become z to negative 1. And this term here, gp over s star, we're going to have to replace e to st with z. Now what we're going to do, we're going to define z of gp of s over s as the following: as gp of s divided by s star when e to st is equal to z. So this is by definition. So if I use this definition and go back, I'm gonna get y of z is equal to 1 minus z to negative 1 multiplied by z transform of gp of s divided by s multiplied by u of z. Or I can write this as y of z divided by u of z equal to 1 minus z negative 1 z of gp of s divided by s. And this is the conclusion that we want. So here we took this system that has a continuous time system in it, and we were able to express y of z over u of z. Okay, let's do an example to see how this is applied, and of course we're going to be using this throughout. So let's say we have an open loop sample data system. And this system has a u star of t, and then we have a zero order hold of a digital to analog converter. Then we're gonna get u bar of t, and then I have a system gp of s is equal to k divided by s plus a. I have a first order system, and then the output is continuous y of t. Then I'm gonna take analog to digital converter, and that is going to give me y star of t. And what we want to calculate is we want to calculate the pulse transfer function. And the pulse transfer function is g of z y of z divided by u of z. And this is gonna equal to y star of s divided by u star of this is small letter, by the way, u star of s, where z is equal to e to s multiplied by t. And from the previous development, we know this is going to equal to 1 minus z to negative 1 multiplied by z of gp of s divided by s. Okay. So in this example, we're going to need to calculate the Z transform of GP of S divided by S. So therefore, if I take GP of lambda divided by lambda, what is this going to equal to? GP is K over S plus A. So this is going to become K divided by lambda plus A. But I'm also multiplying it by lambda, so there is another lambda. Now I'm going to write this as equal to A over lambda. I'm going to do partial fraction expansion plus B over lambda plus A. What is A, capital A, equal to? Is going to equal to lambda multiplied by GP of lambda divided by lambda. Substitute when lambda is equal to 0. And this is going to be lambda multiplied by K over lambda, lambda plus A. Lambda with lambda is going to cancel. And if I substitute lambda equal to 0, I'm going to get K divided by A. And this is the residue when for lambda equal to 0. Similarly, I can calculate B. B is going to equal to lambda plus A multiplied by GP of lambda divided by lambda, which is going to equal to lambda plus A multiplied by K divided by lambda multiplied by lambda plus A. Lambda plus A, lambda plus A is going to cancel. I'm going to substitute when lambda is equal to negative A. And this is going to give me negative K divided by A. And this is the residue for lambda equal to negative A. Okay. So therefore, what I need to calculate, I have GP of S divided by S. I'm going to calculate the star transform of this. And to calculate the star transform of this, this is going to equal to the summation over the poles of GP of lambda divided by lambda of the residue of GP of lambda divided by lambda multiplied by 1 over 1 minus e to negative t multiplied by s minus lambda, lambda I. And therefore, since I know the residues and I know the lambdas, this is going to equal to k over a. This is the first residue multiplied by 1 over 1 minus e to negative t, and I substitute for lambda. The first lambda was a 0, so this is going to be e to negative t multiplied by s, minus the second residue was k over a multiplied by 1 over 1 minus e to negative t multiplied by s minus the second lambda, which is equal to negative a. So this is going to be plus a. Lambda is negative a minus lambda is going to be positive a. So this is equal to k over a, 1 over 1 minus e to negative t multiplied by s, minus k over a, 1 over 1 e to negative t multiplied by s multiplied by e to negative t multiplied by a. Now we're going to calculate the z transform of GP of s divided by s. And if you recall from here, we said the z transform of GP of s over s is going to be equal to GP of s over s star, and we substitute e to st with z. So coming back here, we calculated GP of s over s star, if I substitute for e to st with z, I'm going to get the z transform of gp of s over s. So this is going to equal to gp of s over s star substituting e to st with z. And therefore this is going to equal to k over a multiplied by 1 over 1 minus z to negative 1 minus k over a multiplied by 1 minus z to negative 1 e to negative t multiplied by a. And therefore I can write this as k over a, I can multiply by z, z over z minus 1 minus k over a, z over z minus e to negative t multiplied by a. And therefore g of z going back here, g of z is going to equal to 1 minus z to negative 1 multiplied by z of gp of s divided by s. So therefore here g of z, which is y of z divided by u of z, is going to equal to 1 minus z to negative 1 multiplied by the z transform of gp of s divided by s, which we calculated, and therefore this is going to equal to, I can write this as z minus 1 over z multiplied by k over a multiplied by z over z minus 1 minus z divided by z minus e to negative t multiplied by a. And I can simplify this. This is going to equal to k over a, and I'm going to, z over z minus a is going to cancel with this. So I'm going to get a 1 minus z minus 1 divided by z minus e to negative a multiplied by t. And I can simplify this as k over a, z minus e to negative t multiplied by a minus z plus 1 over z minus e negative t multiplied by a, which is gonna be equal to k over a, 1, the z with z here is gonna cancel, and therefore I'm gonna end up with 1 e to negative t multiplied by a divided by z minus e to negative t multiplied by a. And this is our pulse transfer function. And this will relate the output in my example here, the output y of z to the input u of z. Okay, I'll stop this module here. We'll continue with the next module.